equal to 1 over 2 to the 1 power, which is equal to 1/2. So the coordinates of this point are -1, 1/2, right? So what we can say about this curve is that it rises very, very rapidly on the right-hand side, and on the left-hand side, it decays quickly to the x-axis, right? Now, what we want to do is the following. I'm going to change the color here of my pen. I want to look at the equation y is equal to 3 to the x power, all right? So we would suspect that the graph of y equal 3 to the x power is going to look a lot like y equal 2 to the x power. In point of fact, they both pass through the same point on the y-axis. So they both have the same y-intercept. Here, this is going to be the point 0, 1. And then at 1, so here's one of the points where things differ. At y equal 1, I find that, or at x equal 1, I find that the value of y is equal to 3. So 1, 3 here. And then at x equal 2, I can't really fit this on the graph, but we'd be way, way up here. And my curve would be rising very, very rapidly. So this curve, for values of x greater than 0, the graph of the curve, y equal 3 to the x power, lies above the graph of y equal 2 to the x power. Now let's look at what happens when x is equal to -1. So when x is equal to -1, the value of y, the corresponding value of y, is going to be 3 to the -1, which is equal to 1 over 3 to the 1 power. And that's just equal to 1/3. So here we have a point -1, 1/3. And the graph of the equation y equal 3 to the x is going to pass through that point. And then it's going to decay asymptotically to the x-axis, just as the graph of y equal 2 to the x power does. So we can generalize this. We can say that given a value of a greater than 2, okay, the graph of y equal a to the x power is going to lie above the graph of y equal 2 to the x power for values of x greater than 0, okay? Moreover, when x is equal to 0, the curves intersect. And when x is less than 0, strictly less than 0, then the graph of y equal 3 to the x lies below the graph of y equal 2 to the x. Okay? All right. Now recall also that I ask you to look at the graph of a couple of functions. So the last time in lesson 1, I gave you the function g of x is equal to 2 to the x power plus 1. And I wanted you to graph this. So graph this function. Well, when I'm graphing a function, one thing that I really have to pay attention to is what is the domain of the function. So I want to know what the domain of g of x is. Well, the domain of the function 2 to the x power, that's the set of all real numbers. So I have 2 to the x power plus 1. This is a constant. They both have domains which span the entire real number line. And so the domain of g of x is just going to be minus infinity to infinity, all real numbers. Moreover, we know that the limit as x goes to minus infinity of 2 to the x power, this is equal to 0. So this is really important. This is really important. Tells us that 2 to the x power has an asymptote along the x-axis in the negative x direction. And so what I have here, if I'm looking for the graph of my function g of x, I'm just going to graph the function 2 to the x. And here, I'm going to set this equal to 1 here. So this is 1 comma 2. And then what I'm doing is I'm just shifting everything upward. I'm adding 1 to the function 2 to the x power. So I'm just shifting the graph of the function 2 to the x 1 unit in the positive y direction. So everything is being shifted upward 1 unit in the positive y direction. And so that means that my function, the graph of my function, is going to approach the line y equal 1 asymptotically as x goes to minus infinity. Okay, so this doesn't quite look to scale, but kind of get the point. The distance between all the points on these curves is 1 unit. 1 unit. All right. All right, and then we had a second function, h of x is equal to 2 to the minus x power minus 1, I think. And here again, if I'm looking at the domain of h of x, that's going to be the set of all real numbers, because the domain of 2 to the minus x, the domain of that function is the set of all real numbers. Moreover, if I look at the limit as x goes to infinity, x is going to plus infinity of h of x, which is equal to the limit as x goes to plus infinity of 2 to the minus x minus 1, this is just going to be, well, we know when x goes to plus infinity, 2 to the minus x is going to go to 0. So now I have an asymptote in the positive x direction. And so this limit here is just going to be minus 1. Okay, so here I have the graph of y equal 2 to the minus x. And so it has an asymptote along the positive x-axis. And what am I doing? I'm shifting everything down minus 1 unit. So in particular, this point here, this is my point 0, 1, that's going to be shifted to the origin. And I'm going to get a curve that looks a little like this. So I'm going to draw it a little bit better this time. This is y equal -1, and my curve, oops, I didn't draw it better. Looks like that. So this is over here, this continues upward. And the distance between these two curves is just 1 unit everywhere, which means this line, y equal -1, this is an asymptote. Okay, we'll stop here.